All right, welcome everybody to today's special Solar World Congress at 50 follow-up webinar by the International Solar Energy Society, ISES. We are very pleased to have all of you here, and we are going to get started now. My name is Arabella. I am the Congress's Communications and Outreach Officer here at the ISES HQ in Freiburg, Germany, and I will give you a short introduction into ISES and the work we do, as we have many new participants joining us on the webinar today. The International Solar Energy Society, ISES, is a non-profit UN-accredited membership NGO. Our vision is 100% renewable energy for all, used efficiently and wisely. ISES represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. And ISES works together with like-minded organizations from countries all around the world to advance the renewable energy transformation. There are many benefits to joining ISES, and you can always learn more on our homepage. Some of the benefits are the exclusive and unlimited access to all webinar and past webinar recordings in our webinar archive. ISES members also get free registrations and discounts at ISES events and at joint events. ISES publishes a monthly newsletter where you can follow our progress and share your news. And of course, Solar Energy, our flagship publication, is available to ISES members at a discounted rate. And in the ISES online bookshop, you also find books on all types of solar for a reduced price. For a special offer for today's webinar, we offer all new joining ISES members a 20% discount when signing up as an ISES member. You will receive your personal discount code after the webinar, and you can always sign up on our homepage. So we welcome you joining, and for all of our members, we thank you for your support. Now, for a quick word on the Q&A session before we start the webinar. There's going to be a Q&A session where we're going to answer all of your questions on the presenters' presentations. This is going to be at the very end of the webinar, so we're going to have a cumulative Q&A session for all of the presentations. When sending in your questions in the chat box, keep your questions short and precise and write who your question is for. Now, it's my great pleasure to introduce you to the moderator of today's webinar, Jeff Stapleton. Jeff is a long-time and trusted ISES board member, and he's also the chairman of the Solar World Congress at 50 celebration event. So Jeff has been with this event from the get-go. It's been very much his brainchild, and we really appreciate all the hard work Jeff has done on this event. So Jeff, thank you very much for joining us, and the floor is yours.
Thank you, Arabella. Yes, and good evening, afternoon, morning to everyone on this webinar, and thank you very much all for joining. Yes, just very briefly, SWC50 was celebrating that in 1970, what was deemed as the very first Solar World Congress was actually held in Melbourne, Australia. And so we were originally hoping to have a celebration in Melbourne last year, 2020, but we all know what prevented that. So we actually had an online event just literally this time last year. And then we also have been doing this by follow-up of a number of workshops. What also came out of the SWC50 event, and you can find this all online, we've developed a booklet which went through a very brief history of solar in the different applications by decades. And there is now an online solar museum, which is probably a bit of a brief view of the booklet, but it also does include videos, and that museum will be an ongoing part of ISES, with it being a major update to it next year. So on that point, we won't hold back. We'll move in today's. So this being is the final official event of SWC50, and we thought it was most appropriate that with what is happening with the world and the move towards zero emissions, to have a look at how the grid will look like in the future. So I'd like to introduce our first speaker for today, Debra Liu. Debra Liu has been involved with this industry for many years, as you could see through her involvement there. I first met her in her NREL days, probably about 20 years ago, I would say now, Debbie. But she's now as the Associate Director of ESIG. Prior to that, she was with GE Energy Consulting, and she spent 16 years with the National Renewable Energy Laboratory. And she's immediate past chair, very relevant to today's topic, of IEEE Power and Energy Society's Wind and Solar Power Coordinating Committees. Thank you very much, Debbie, for joining us today.
Thank you so much, Jeff. And I'm really honored to be here and to be helping to celebrate the 50th anniversary and being part of the SWC50. Okay, I'm gonna try and share my screen here. Can you see that?
Yes, looking all good.
Great, thanks. So I thought it might be fun to talk about some myths that folks have about solar and the grid. And what I'd like to talk about is the importance of the grid and supporting high levels of solar to decarbonize the system. So before I get into it, I just want to briefly say ESIG, the organization that I'm with right now, Energy Systems Integration Group, is a forum for the industry to come together to address technical challenges for transforming energy systems. We do a lot of education and peer learning, and I urge you to go to the website where you can access workshops and webinars and reports. And also, we're part of a global organization where we lead work with NREL, with 6 leading system operators around the world, so including AEMO in Australia, CalISO, ERCOT in the United States, EnergyNet, Our Grid, and others. So we're also working globally to try and help bring together best practices. So, all right, let's start with the myths. One of the myths that's out there about what we need to decarbonize is this idea that maybe we don't need transmission, that we could do it all with rooftop solar. And what I'd like to point out about this myth is that the first thing to note is that electrification is going to significantly increase demand. So I don't know if you can see my pointer here. Let's see, I'm not sure if there's a way to do this, but in this top right graphic, and I'm going to focus in a lot on the United States because that's what I know best. This is the electricity consumption of the United States about today, about 4,000 terawatt hours. And what we see is, depending on how electrification happens, how fast, and whether we move to generating hydrogen and other needs for electricity to help generate renewably generated fuels, we could be looking at a doubling or more of electricity consumption. And that's what some of these projections are showing. So electrification, first of all, is going to significantly increase demand, and rooftop solar is definitely going to contribute, but it's not going to be sufficient on its own. So if you look, for example, at where this orange arrow is pointing, it's about 1,400 terawatt hours. That's what NREL estimates technical rooftop potential in the United States to be. So even if we could reach all of that, it's not going to be enough. What studies are looking at is that we may need 1,000 gigawatts of wind and solar, maybe even double that, to meet clean electricity and clean energy goals. So there's going to be a significant build out of new wind and solar. Distributed solar is definitely going to be part of it. It's not going to be enough on its own. We're going to need transmission to deliver a lot of this wind and solar to load centers. And we're going to need transmission for more than just the interconnection of these new resources. We need transmission for resiliency, for example. So on this left, this is showing the winter storm Uri that hit us in February of this year. And what you can see is that this is the market interface between PJM, shown here on the east coast, and MISO, shown here in the middle of the country. And you can see transmission constraints limiting how much MISO was able to import from PJM during the system. So during the event, MISO, they were importing about 13,000 megawatts, sending about half of that west to SPP and to others. Now Texas, which is down here in the south, is islanded from the rest of the US. It's got limited DC interties to the rest of the US. It was only able to import up to 800 megawatts from SPP. And during that event, as you may know, ERCOT was unable to serve over 23,000 megawatts of firm load. So really significant shortages that could have been ameliorated if there were more interconnection with the rest of the United States. Now, transmission can also reduce the amount of generators that we need to build. For example, by connecting their transmission to connect to diverse regions. So as an example, on the top right here, this is looking at resource adequacy in SPP. And as they built out their transmission and expanded their footprint to connect diverse regions with diverse load and resources, they were able to reduce their planning reserve margin. So how much extra capacity needs to be built from 17.6, 13.6 to 12%. And then that last step saved $90 million a year by avoiding the need for new power plants. And then on the bottom here, this is looking at deliverability. We need transmission to deliver ancillary services like ramping capability. This is from a MISO study. It looked at ramps due to high wind and solar penetrations. They looked at which generators could be providing these ramping services and whether or not those services could be delivered, and found that they actually needed to build more transmission to be able to deliver those services. Okay, on the flip side of this first myth is myth number 2, the idea that we can do everything with cheap utility scale solar and that we don't need distributed solar. So this is sort of the opposite argument. And the first thing I'll point out is that nearly all the national level studies out there look just really at the bulk power system. When they consider distributed energy resources, they typically consider them in terms of a cost trade-off of building distributed resources versus, say, utility scale PV plus transmission. As far as I know, Vibrant Clean Energy, shown here, is the only group that is including optimization at the distribution interface in their national studies. So the idea here is that if we're going to electrify transportation, heating, and other end uses, this is going to increase loading on distribution feeders, and upgrades may be needed. Now, if you think about it, maybe that's not a big deal for a few distribution feeders, but when you think about the ubiquitous distribution infrastructure out there, it would cost a lot to upgrade all of that. So they include this cost in their optimization, and what that ends up doing is moving from this graphic on the left, where this is what feeder demand might look like normally, to the right, where basically feeder demand is sort of squished. The peaks are shaved and the valleys are filled. And so it helps to reduce the need for distribution upgrades. What happens when they include this in their model? So what they're optimizing across is generation, transmission, and distribution for decarbonization for future scenarios. What happens is it shifts some of the utility scale PV and some of the utility scale storage into distributed scale PV and distributed scale storage. And interestingly, in this process, so going from, say, this third bar to this fourth bar here, you can also see that more transmission gets built. And this is because you're still going to need to manage excess solar generation, even with battery storage, and you're still going to need to plan for multiple cloudy days in a row. So interestingly, even with this move to more distributed energy resources to help manage distribution upgrades, it builds out more transmission. And then, of course, you save tremendous amounts of money by optimizing across this distribution interface as opposed to just ignoring it in the future scenario development. Okay, the third myth is that we should do it alone. So the idea that decarbonization is going to be cheaper if we do it alone. So this is a recent study of MIT from Brown and Boterud, and it looks at the value of transmission expansion and coordination for increasing geographic levels. So start with just expanding and coordinating within a state, and then within a region, and then between regions, and then nationally. And do this for 100% clean electricity. So this right-hand graphic is showing transmission capacity increasing as you go from a state-by-state approach to a regional approach to a national approach. And that's what these 6 bars are. And on the bottom left, these same 6 bars are showing the cost. So as that transmission capacity increases, we're seeing the cost of delivered electricity decrease. So what we find is that the every state for itself approach, shown by this top blue bar, is costing twice as much as the nationally optimized and coordinated approach. So there's a lot of savings to be had the larger the region that you can coordinate your transmission planning and your operations over. Okay, myth number 4. We can do everything with solar plus storage. We don't need transmission. So this is another idea that may be out there, that solar plus storage is all we need. And to some extent, there is competition between transmission and storage. So to some extent, there are similar services that they both provide. And this, again, is from that same MIT study that I just mentioned, showing from left to right, going from a state to a regional to a national approach. And what they find is that as you increase the geographic size and you increase the transmission capacity, you can see the storage energy decreasing and the storage capacity, that's shown in this dark green in this third graph, decreasing. So there is some competition here between the transmission and the storage capability. But we also find, and you look at this graphic from the MISO-RIA study, that if we allow the model to optimize across transmission and storage, that gives you your optimal solutions. And that's what you would expect, that if you allow for the largest basket of solutions, you're going to get the cheapest solutions. And that's what they found in, these were medium level wind and solar scenarios, and they were looking at energy balancing over the course of the year. And in this MISO study, they found that if they allowed the model to optimize across transmission and storage, it built about 0.5 gigawatt of storage plus transmission. And if they only looked at storage-only solutions, and you can see here on the top right, that the storage-only solutions built out 30 times as much storage, and the cost was many times what the optimal cost was. Interestingly, the transmission-only solution was only marginally more expensive, but the optimal solution was allowing for both transmission and storage, essentially allowing for storage to provide the flexibility for wherever that flexibility is needed on the system. And then myth number 5, that the grid will be too expensive. And there's been some recent articles, for example, on this in the lay press, I think in the New York Times. And what we see is that it is true that the cost structure is going to change. So this graphic on the left from the EIA is showing in the dark blue, this is generation costs. And then in the gold, it's delivery, the T&D costs over time. So this is utility spending over the last decade. And you can see that power production is getting cheaper. And we all know that wind, solar, batteries, these costs are going down. At the same time, delivery costs, T&D costs are increasing. Now, I would say that we expect this to occur. We expect this to occur because wind and solar, those costs are getting cheaper. They have zero fuel costs. And we expect that the grid infrastructure costs that are necessary to support more wind and solar, as we've talked about in the last 4 myths, that infrastructure is going to increase. I would also add, though, that just because we're changing where we're spending our money, that doesn't mean that electricity prices will increase. And you can see that here on the right, where this is showing electricity prices in the US over the last decade decreasing. So yes, we're going to change where we put our money, but we expect that prices aren't necessarily going to increase as a result of that change in cost structures. And then I would also add transmission costs. A lot of these studies are finding significant investments in transmission, $200 billion to decarbonize electricity, maybe $350 to decarbonize all of energy economy wide. Those are big numbers. But when you're talking about putting in a terawatt or 2 terawatts of wind and solar and then storage on top of that, it turns out the transmission costs are tiny in comparison. So this graphic here on the left, this is from that same MIT study that I had mentioned, and it's showing transmission costs being $5 per megawatt hour and being less than 10% of the delivered cost of electricity. And then this middle graphic, this is from NREL SEAM's study, and it's showing the 50% renewables case. Most of the cost here is fixed and variable generation costs. Transmission costs are really very tiny. And then on the right here, this is from that Vibrant Clean Energy group that I'd mentioned earlier. They're 100% clean energy economy-wide scenario. And what we're seeing there is, again, significant investment in fixed and variable generation, transmission costs being really a tiny sliver here. And then the yellow on top is the distribution cost. Now, I would just caveat this by saying, again, they're the only model that I know of that looks at the distribution interface in these studies. There's a lot we still don't know about what's needed in terms of costs here. And this was the first study to look at this. So I think we need to have a lot more study work on the interface of transmission and distribution in these decarbonization scenarios. And with that, I will end my talk and hand the floor back over to you, Jeff.
Thank you very much, Debbie. That was very good and very informative of what is happening in the US. Now we'll move back across the water to Australia, to Scott Chapman, who is the group manager of AEMO. For those who are outside of Australia, AEMO is the Australian Energy Market Operator. So basically, and Scott will explain this in his presentation, but looking after what we call a national grid and its operation. And he's had over 20 years experience in utilities, business and banking across Europe, Asia, New Zealand and Australia. He's had a very broad range of activities in the utility sector over this time. He's recently focused on the increase and improving the role distributed energy resources play in the Australian market. And thank you, Scott, for being available this morning and to present on what is happening in Australia. Thank you.
Good morning, everyone. Just trying to work out, here we go. Show my... Okay. Can everyone see that?
Yes, Scott, I can see it.
Okay, so as Jeff just said, Australian Energy Market Operator operates the electricity grid on both the east coast of Australia and the west coast. The blue patch in the middle you see there on the slide, there's not much there, so there is no grid per se. The two markets are separate, and as we can see here on this slide, you can see the actual grid itself. So the situation in Australia is that we've got rapidly rolling out solar, and we're starting to see storage increase. And so it's a very, very positive story for us in Australia as more and more energy is coming from rooftop solar. In one state in particular, South Australia, the bottom middle state, last year we were getting up for high 90s, and I think during the course of this year we may have even gone above 100% instantaneous energy coming from solar PV. That has though presented some challenges for us, because what happens, as most people on this call will know, is that during the day, as the solar generates, we reach a situation, what we call of minimum demand, where the rooftop solar is meeting almost all the needs of the loads, and therefore the remaining load to be supplied comes from the synchronous generators on the system. And the challenge for us is that that demand goes so low that we don't have sufficient ability to control frequency in a reliable fashion at those points of low demand. So that's one of our primary issues that we're grappling with at the moment in what is otherwise a very good news story, and something that we're happy to embrace because it means we're trending in the right direction as regards climate change and whatnot. So this is a forecast then with regard to minimum operational demand in South Australia, where the solar penetration is the highest in the country, and we're predicting that this year that minimum demand will actually go negative, and that is to say that will be more than 100% instantaneous energy coming from rooftop solar. And fortunately, from 9 times out of 10, we can handle that because all the different states are interconnected on the east seaboard. So I might just, at the risk of making you dizzy, come back to this slide, and you can see that South Australia has a long pink line which connects into the bottom right-hand corner of Australia. And so what happens when there's greater than 100% instantaneous energy coming from one given state, that it can export its surplus to the other states. And also we can rely on the synchronous generators in the other states to some extent, as well as South Australia, to stay online and maintain frequency. The issue for us though is when those, what we call the transmission interconnectors, when they trip, and then we have islanded situations where each state is separated from the other. And that's when our minimum demand issues really step up. So the main thing for us now is how do we address those challenges? So we're working through that at the present time with each of the states. So very similar to the United States, indeed Europe, though we're one country, they're effectively separate governments that need to work together. And so that becomes a challenge to get each jurisdiction ready for the ever-increasing solar. And I should say at the moment we're around about 14 gigawatts off the top of my head of solar PV in Australia, and we expect that will triple over the next 5 to 10 years. And the primary reason for that is solar is just the cheapest source of energy. And so consumers are opting to install solar on their roofs, and we're starting to see batteries be installed in the garages. So it is the nirvana that we've all been hoping for the last 30 years. So the challenges we've identified with this high penetration of solar PV are that we see unintended disconnection. So we've had a fair bit of consternation, is the word I'd use, about the performance of various OEMs inverters. The OEMs, of course, manufacture to protect the onboard electronics that the consumers have purchased. And so sometimes we see that those inverters probably disconnect from the system more quickly than we would like. The other issue is then, as I mentioned earlier, the insufficient load to operate the necessary units for essential services. And so that means that because minimum demand goes so low, so you might have a synchronous generator, say in South Australia, it's 300 megawatts, or indeed, I think there's 600 megawatts, and then you've only got 400 megawatts of load. So there's a risk that we lose synchronous generation control. So it's working out how we handle that. And then the other one is under frequency load shedding. So the issue there is that so typically what we've done for under frequency load shedding is we have feeders on the distribution network set up to automatically disconnect from the grid. The issue becomes, as solar penetration increases, what you may have assumed 10 years ago was a feeder that was a net load, you find that it's a net generator. And so you've got to be careful about the implications for shedding entire feeders as to whether you'll actually make the problem worse or better. So next slide. So this shows, this graph at the top shows the issue we have with unintended disconnection of solar in response to a grid disturbance. And the graph at the top right shows that it was an event last year, or sorry, the year before in Western Australia now. And right up until 1450-48, we had lots of sun, the solar generating, and load was around just under 1340. Then we have a disturbance on the grid. In this case, I'm not sure what this disturbance was caused by, but the solar is shaken off, and we see additional load come onto the system, and then you get the frequency response spike, and then slowly the other generators pick up to absorb that, absorb the initial frequency response, and the system settles out eventually at 1420. And I should say that's generation, not load. So in other words, really you're seeing, you know, in this case it was Western Australia, which is a smaller state, so only about 100 megawatts of difference. But if you come on the eastern states where numbers are higher, that step change over the course of a couple of minutes can be several hundred megawatts, which is a system operator challenge. The other thing we've done, sorry, and maybe I'll say before moving off. So one of the things we're doing at the moment is working through with industry on setting up a mechanism to handle this situation. And we're moving slowly over the next couple of years, we hope, to a system of controlling operating envelopes for solar, subject to industry joining us on this journey. But the concept at the moment is that we would have a thing called dynamic operating envelope. That means that the distribution network can dynamically control how much solar can be admitted to the grid. And normally that would have a focus on maximizing the export, but there will be these occasional, and when I say occasional, I'm talking maybe, you know, of the order of once, twice a year, where the market fails in the sense of responding to price and other signals, and we have to step in, and as the overall transmission generation operator, we ask the distributors to just throttle back the output from solar just so that we can keep frequency under control. And that would be the idea of the dynamic operating envelope. And that brings with it a whole bunch of technical challenges around how do you get an entire ecosystem to talk to each other? How do you get the various market players to interact with each other? And the other thing there to note is just that, you know, we're entering the age of democratization of energy. And so anything we do needs to be heavily consulted and agreed with all stakeholders, which now become individual residential consumers. So it's a real exercise in stakeholder engagement, and it's a good thing. It's a good problem to have, you know, getting everyone to participate. So, of course, that's me being the energy dork that I am. The other thing we've done is to try and amend some standards, and this relates to the unintended disconnection of inverters from the grid. And in particular, we made a change to the Australian standard which relates to inverter performance and required there be certain tests. So in particular, we called it the voltage disturbance ride-through test, which we've upgraded the inverter standard to document, and now manufacturers are starting to manufacture to that new standard and undertake those tests, which has been good. We're finding though that that's not necessarily been the panacea we were hoping for. It has helped a lot, but we've got issues of, you know, there are legacy systems out there, and there are other things that we're starting, as we effectively peel the onion, you know, we address the biggest cause and we're now down to the next, and I'm sure now after that there'll be another problem. So it's just a matter of having a lot of technical capability and being able to apply that technical capability to address these issues and move to the new paradigm that we're all headed to. And one of those things that leads into a conversation about data. So we're working with a whole bunch of suppliers in the energy ecosystem to collect data on performance of inverters. And this is just a heat map, which shows where we're collecting data, where we've seen problems on the East Coast. And we're working with universities. That's what you see there, the third bullet point down, a reference to Project Match. So that's University of New South Wales in Sydney, working with us to collect and collate data and then understand, gain insights from that data in terms of inverter performance. We're working with another bunch of innovative companies. We have in Australia a company named Solar Analytics, and Tesla now, as their Powerwalls meet more and more success with the market, rolling out, and we're collecting data from those Powerwalls as well with the Corporation of Tesla. So this next slide just talks about the issue we have around min demand, and where we see that we're going to have a problem moving forward. So you can see there at the bottom right, we think the system, you start to have problems with the system once you get down to around sort of 6,000–7,000 megawatts. And we anticipate that we're going to really enter that period around 2024, 2025. So, and the interesting thing for us in Australia is that every year we produce this same graph, the risky period comes in closer and closer and closer, and that's because we've, as a nation, really been surprised by the extensive and rapid uptake of solar PV. And so where we thought we had a problem that was maybe 10 years out, say 5 years ago, that, you know, comes in closer and closer every year. So, and this slide's just talking about, you know, what is the perfect storm, if you like, which triggers a minimum, what we call min demand day. And so we, the energy geeks among us, watch for weekends, which is in our October. So late spring, when you get really mild weather, and so on a Sunday afternoon, no one's got their heater on, no one's got their air conditioner on, industry is shut down, and that's when we hit minimum demand conditions. So we
could we start rounding up with your last challenge now, please?
Yep. So yeah, as I discussed, it's emergency backstop PV curtailment is our main challenge now, and we're working with industry to come up with solutions that will work for ourselves and industry. And then the last one, which I mentioned, was under frequency load shedding, which is where we disconnect entire feeders on the distribution system, and then working out which of those feeders are net generators and which are net load, so you work out whether you're going to exacerbate or improve the problem. But I might leave it there. There's a ton of other slides to go through, Jeff, and I might hand back to you at this point.
Thank you. Look, thank you very much, Scott. Being biased, I probably would have liked to let you continue on, but we have got other speakers we've got to have a look at. So now we go back to the US. Arabella, can... Arabella, we have... And now I'd like to introduce Jessica Lau. She's from NREL. She's the Group Manager of the Grid Systems Group within the Grid Planning and Analysis Centre there at NREL. They spearhead the efforts on modelling and informing power system reliability, resilience and economics. She previously been experienced in the bulk and distribution system planning, and currently leads teams support communities in their energy systems transition through decision support modelling analysis. Thank you very much, Jessica, for joining us today. Afternoon there, and look forward to your presentation.
Great, thanks so much, Jeff. Hi, everyone. Let me pull out my slides here. Great, here we are. So today, I'm so happy to be here to talk to you all, and looking forward to the Q&A and any questions through the chat as well, but to share my own perspective on future power grids. As Jeff mentioned, I have background in, spent the first part of my career at bulk level planning at an ISO, and then transitioned to a distribution utility, planning the distribution side of the grid, and certainly looking at things that Scott had mentioned as well in terms of under frequency load shed, and how to integrate new technologies. And that's why I'm really thrilled about joining NREL over the past 4 years, and being a group manager as part of grid planning and analysis. My focus is very much on connecting the technical innovation and the solutions that are developed and bridging them into answering today's problems and today's issues to solve those now. So I feel like an unfortunate place to connect. I spent a lot of time listening, understanding what the current challenges are within the grid, and then helping bridge that gap there. And so with that, I work at the the increment here, at the National Renewable Energy Laboratory in the US, of which we focus on these 4 main areas of research. Me specifically, as I mentioned, am in grid planning, specifically in energy systems integration. So not just the grid itself, but in transportation and buildings and efficiencies and other technologies, how does that all come together? And so not only are we always studying what is the impact of changes and decisions we make, but we also think about the systems and innovation of, if we think about the future grid, what do we need to start working on right now to make sure that we have that ready in the future, like building a new model or some new data sets. And so with that, I'm going to share 4 specific themes that I'm identifying in my perspective of future grids for us to discuss today. The first one I'd like to start with on the top left is certainly to acknowledge change is here, change is coming. And in the US, not only winter is coming, right? So the way it's been doesn't mean it's the way it will be. And I think that's key to say. Some people might immediately say, oh, of course. Some people might say, well, I mean, maybe not, right? And I think maybe the more concrete example, what I want to pull up here, is that people have evolving expectations of the grid. And so if I use the right side as an example, these are some examples of how people and customers are talking about, or companies, commercial, industrial customers as well too, right? That talk about their expectations of the grid. So if we start at the very top, someone might say, I never ever want to lose power. However, we know there's a cost to a request like that. So on the right side, somebody might say, hey, but I want you to decrease my bill. If we start back and moving to the left, right in the middle, can it be 100% renewable? I want to have say in where my energy comes from. And then the top left, oh, what about, can I choose the exact technologies? What if I myself invest in solar panels and batteries? Can I never ever pay another electric bill, right? So these are representations of people, their thoughts, their connection, their learning of the grid, but also the evolving expectations of it. I think that's really important for us to talk about in this theme of that things are not going to stay the same, because people have this evolving expectations. And so with that, I'm connecting it to what we might do about that. And so one of my recommendations is in terms of expanding the way we do planning in a way that I'm framing here as multi-objective, multi-value, meaning we are able to include these values broadly across how people are connecting to the grid. I mean, traditionally, it was about reliability. I don't think that's going to change. Certainly, we want electricity, we want reliability with it, right? But as an example, in the US, there are at least 30 different states that have renewable portfolio standards, and at least another 5 states that have clean energy standards. So this is certainly, for example, another objective that we could say that is added on in pairing with reliability, right? And not to say going forward, some may be more important than others, but I think the bottom line will be, if we don't address them in a holistic way, in an inclusive way all across, we know that when we're planning for the grid, it won't be representative of the people and what their expectations are. And so that's, I think, a key piece about how we'll be moving forward. The second one I want to share is about how we're going to use technologies and all the different assets that are part of the grid. And I want to make the theme that, and share the theme that we'll be doing this really flexibly and interchangeably. I think, for example, from Debbie and Scott's presentations, you've seen that the grid is certainly operating in a different way than it has been in the last 30 years, for example. And what that means is that not only do we need all the technologies, advancements, innovation, and everything ready to go within the grid, but that paired with the changes that we're looking at, these evolving expectations, and also profound uncertainty about what the future might look like, means that we will need to harness all the technologies we have available to us, but not only that, be unconstrained in our thinking about how we're going to use them. So in ways that I think people are looking at how different devices to the grid, like solar plus batteries, for example, can provide different kind of services, right? That a wind turbine can provide traditional services like balancing the grid that might have been provided by a thermal generator. those are all things that I think start to demonstrate how we're going to expand the spot of flexibility over time, but that continuing forward, especially in this mindset of research, is that it's my primary role. It's important to know that all of our collective perspectives of the future grid will best support how we think about innovation in designing new technologies, approaches, and incentives to make that happen. Because certainly, if any of us had the crystal ball, there would be great things to do. But I know only our collective perspectives are likely that crystal ball that at least we can prepare for it. The third one I want to talk about in terms of themes is that incentives can show up in many ways. I think very often, let's use the example of electric vehicles, right? When somebody buys an electric vehicle, their primary purpose for the majority of time is for transportation, to get them from one place to the next. Maybe some secondary objectives might be around, where the power is coming from, how it's made, what the cost is to them, how cool a new car might be. However, if we think about those objectives, usually the top one is not, I bought an electric vehicle to be a grid asset, to be an active part of providing energy storage to the grid. Now, it could be their secondary, their third, or other objective, but it's unlikely to be the customer's first primary objective. And so I want to use that example to demonstrate that traditionally, to talk about, like, traditionally, all grid assets are utility or developer owned to some extent, where their primary objective is to be a grid asset. A substation is installed to be part of the delivery infrastructure, right? Same thing with a generator, same thing with transmission lines, distribution lines, right? They're all designed primarily to be part of the grid. And what we're talking about here in the evolving expectations of customers, because we have devices and technologies now that can serve our primary use. Like in a house, you could have rooftop solar, and your primary objective could be selling it back to the grid, or you could use it to heat up your water or charge your battery or so on. This has really expanded not only the purposes and objectives, but in the flip way, the incentives, right? Because at the end of the day, nothing is really for free. And so when I talk about, the alignment of incentives here is to, one, I think, acknowledge what the current incentive mechanisms are. They could be within markets, within tariffs or taxes or rates, things like that. And that won't be the end, and that won't be the only pieces. And financial incentive also won't be the only thing that will drive people to change or contribute to the grid, right? That's why many demand response programs across that I have experience with across the US, right? At some point you reach a saturation level, because if you've asked somebody in the middle of the summer to turn down their AC, there's only so many times or so many days in a row you can ask of that, and then they'll ignore it and they'll say, well, I personally can no longer, satisfy my safety by not having the AC running anymore. Just as an example, and same thing for manufacturing businesses and so on, right? They still have a bottom line to meet. And so when you think about incentives, it's likely, like this picture here, like, it's not just going to be one thing, and it's going to come in all different flavors. And the reality is, just like the technologies, we're going to have to use this in a very flexible and adaptable way to make sure this works. The final example I present here would be in the development of technologies, or working with, for example, new construction of buildings. More and more of the future of the grid, energy systems will be interconnected in a deeper way. And when I say energy systems, I'm talking about the grid, but I'm also talking about electric vehicles, transportation, mobility, I'm talking about buildings, the way where we live, how we go to work, when we work, and all those things together mean that if there is no alignment across the institutions, across the objectives that we have, means that we'll all individually go in separate ways. And certainly there are many different technical studies that say, oh, hey, like, increasing coordination across different geographic boundaries in one sector can bring benefit, but same goes for across different energy sectors as well. And the final one, and perhaps the most important one, which is why I want to end here, is that the theme I want to present to you is that people are the center of the grid. I use this picture here because I think about what comes to mind when you see this picture. Like where could it have been taken? Maybe a football game, maybe a tech company releasing their new phone or their new technology. What I do know in personal experience and talking to others is that this is unlikely to be the picture of a utility rate case meeting or the town meeting when a new transmission line or distribution line is to be built. That's a bummer to me, but I would ask the question, why couldn't this be the community, the alignment that we get in the future? And so this is how it all connects to me, right? Because we started with the way it has been doesn't mean it's the way it will always been. So I understand that there can be objections to building transmission lines, right? Because of where it's going through, or where a new substation gets put, because there's noise and environmental impacts on that. But it doesn't mean that our relationship with people and customers of the grid has to stay the same way throughout. And so when I talk about people are the center of the grid, I think it's not only that they're part of the decision-making process and and that people are part of understanding how decisions are made, but that they get to be a part of it as well. I think in addition to that, many of the elements I've talked about in terms of representing people's interests, right? Like these are all the things that with the proper alignment, we're not only representing people, but we're also ensuring people have reliable power, which has always been the #1 case of the grid is that is what power is for, right? To support each of our livelihoods and well-being. And so with that, I'm going to close with a final thought on this slide, which is that it is, broadly speaking, in the world, it is not universally agreed upon that electricity is a fundamental right that people have. And so if I use that as an example, and whatever the objective that you or your local community might want, is that the assumptions we make about people's right to electricity trickle past into the way we plan for the grid, like having standards about how often power can be lost, how much contingency and reserve we would hold within the system, and then ultimately the direct experience of people with the grid. And so these are pieces that these fundamental assumptions will drive the remaining process of the grid. And so that's why it's important to talk about what we're doing this all for. What is the grid for in the first place? And so that's my final proposal to you in terms of a theme, which is people are the center of the grid. In closing, I wanted to summarize the 4 pieces that we talked about today. And in the interest of time, I will kind of leave this up for a moment here in terms of, again, the way it's been doesn't mean it's the way it will be. We'll be using technologies flexibly and interchangeably. The third is that incentives can show up in many ways. And finally, that people are in the center of the grid. I thank you for everyone's time today. Look forward to our discussion. If you want to dive deeper, one of my collaborators, Ben Hobbs, and I documented in terms of challenges that are broadly experienced, state-of-the-art technologies or models or data that is tackling these issues, as well as recommendations for further development. So those will be in the materials as well. But I thank you for your attention and time. Thanks.
Thank you very much, Jessica. And that was a very good overview of the different ways of looking at the grid and not just a technical way of looking at the grid. So thank you very much for that. We enjoyed that very much. We'll introduce now our last speaker of the day, also from the US, Ferreira, and from one of the other national laboratories in the US, the SANDIA, and she's the manager for Renewable and Distributed Systems Integration Program. It promotes the R&D of the technologies, so a lot of bit of similarities in some of our talks today, but it's given a different perspective from different locations. She has been with the RSD beginning in 2011, and prior to that she was involved with energy storage analysis laboratory at SANDIA, and working on DOE office electricity programs. Thank you, Summer, for joining us today, and we look forward to your presentation.
Thank you so much, Jeff, for that introduction. And thank you to the committee for the invitation to speak to you today. Can you see my slide?
Yes, I can.
Oh, okay, great. Thank you so much again. It's a pleasure to speak with you all today. If you're tuned in today, you likely are invested in and aware much about the solar future, know that the proportion of new energy generation is increasingly coming from solar and other renewable sources. You also in your day-to-day life are no doubt aware of the dramatic increased dependency we have on electricity for all aspects of our lives. Of course, I'm speaking from a US-centric perspective in my talk today and using my own opinions, but I think we're seeing this widely. And at the same time, climate change and the commensurate severity of weather that makes the electric grid more susceptible is occurring, and therefore we have to think about designing the future grid, balancing sustainability and resilience, and hopefully in a way that is not at odds with one another. So we think a lot in my area of research about resilience. We put a resilience kind of spin on looking at the electric grid. We have a very people-centered view, so I appreciated the end of Jessica's talk, and that's a lot of what motivates our thoughts. And then again, with the resilience focus, we think a lot about islanded, remote, rural communities that are not as served by the electric system. They're more vulnerable electrically, and also often the people in these communities can be more vulnerable. This was dramatically displayed in Puerto Rico, where, sorry, I flipped ahead, but the electricity the day before Hurricane Maria shows the lights up across the island, and then dramatically reduced, not just the day after, but for months, even years. Even to today, there are areas of the grid that are not fully back up following that catastrophe. So we look at, a people and electric focused view to understand what the needs are in especially resilience scenarios, times when the grid might be down for a sustained period, when there's other compounding factors that are making a society more vulnerable. And how do we build in resilience? And also with the lens of how do we do it in the most sustainable way possible? Because often resilience comes with energy sources that are not as renewable as wider improvements in the electric grid. So by thinking about resilience, our previous manager used this great example of the International Space Station. It is a resilient electric system. It sees 16 sunrises a day, and it has to stay on to maintain the well-being of the people on board. And it uses a combination of solar and battery. So it's a great motivator as we think about building resilience into systems when we really need that. So a big motivator, of course, is the electric system, but the grid is it's a keystone infrastructure, but it's central to a web of interconnected systems that support life as we know it and expect it to be in much of the world today, from telecommunications to transportation to water, heat, shelter, etc. And what do we want out of the future grid? We want a grid that is sustainable and decarbonized, but we don't want to lose our reliability. We want the grid there when we go to turn on the lights. We want it resilient. We want it to be able to withstand and come back from major events. And we've always wanted it to be equitable, that is more of a concerted effort, at least in the United States more recently. We have to consider the people and who's being affected, and of course, cost. We want all of these things. Again, the team of researchers I work with think a lot about the resilience, so extreme events, and what are the consequences of those, and then how do we value the resilience that you might build into a system, because it's not something you can easily put a value on. So it's really hard. It kind of speaks to some of the last things again that Jessica was talking about, is how much should we expect electricity? Who expects it? And what is it worth? Because the more you build resilience into a system, the more costly it can be. And just as a little bit of a overview, reliability, of course, is focused on just the grid being there, not having small perturbations. A squirrel chews through a wire, a branch falls, or a tree falls on a line. You might get a short outage of 1 to 2 hours is typical in the United States. And those are caused by these small things. But then the consequences go up as the time of interruption goes up. And then we're getting into these low probability but high consequence events that is what defines resilience. So how do we approach this, knowing that we are seeing more and more frequent events that are large scale, that are having increased costs over time? And we see this continuing into the future. And how does it affect people? So of course, resilience is the ability to prepare, withstand, and recover from disruption. So we have to look at all of those aspects when looking at how to address major accidents, attacks, or natural disasters. How are we going to go about this? I'm not going to go into this much. We heard a lot in our first talk from Debra, who gave a really good primer on this question of transmission versus distribution. The short answer, I would agree, is you can't have all of one. You might have seen more recently the Biden administration is really betting big on transmission. We likely do need to really upgrade our transmission lines and look at large PV wind farms. There's still going to be distribution, and often that distribution is something you can leverage or design, especially in resilient scenarios, in addition to more interconnection on the transmission side. So those can work hand in hand when we think about the grid of the future. So whether we go predominantly with large wind farms or rooftop, a combination, of course, is where we're going to be somewhere. We've come a long way. We have a long way to go, especially compared to Australia. What a great talk from Scott. We have a long way to go in the United States, but we are seeing more and more. So back to this resilience. So building energy nodes is, or resilience nodes, microgrids that can come back up if the wider grid goes down. As I said, touched on at the beginning, when resilience nodes or microgrids or just backup generation on a building are put in, they're much more likely to be a carbon intense source of generation, not so much PV and wind as the wider grid, just due to the nature of the way those get considered, financed, and put in. But we can put PV in these scenarios, and then that PV can be used in a good day when there's not a grid outage to support the grid. And of course, there's decarbonization and sustainability benefits. So when can we look at these? Critics will say, but PV is vulnerable to natural disasters after Hurricane Maria, especially. There was issues with PV and wind being damaged. And we also saw criticism in the Texas outage of wind sources. Of course, those weren't equipped with cold weather de-icing or heating options. So we can always have a vulnerability of our generation in natural disasters, but we can also plan around that. I'm just going to talk briefly about a little bit of what we do at the National Lab, and across the other national labs do similar work, of course, in looking at grids, understanding how they work to work towards the grid of the future. As you get to more distribution, more demands, increased electrification, increased loads, variable load profiles that might be new as we increase EV adoption, for example, understanding those grids and planning around the needs of those grids is critical. So we work a lot with specific real communities. We might take their electric network like this small village in Alaska, that the whole village has a peak load of 600 kilowatts. It's not part of a wider grid, so it's really an isolated system, and it, needs to be available to its citizens. It's based partly, at least, on wind and also on hydro. That has backup diesel as well as backup batteries in recent years. So we've modeled this and we bring it into our lab, and we put hardware into the loop, so we put real assets and see how the grid can handle outages. We study the problem of resilience and how it affects the electric system. We do a lot of this work on the electric system, but again, back to the people side, we're increasingly trying to look at not just how does the grid go down if there's an outage, but what is the real impact on people? So some of our work has gone towards this performance-based metric of social burden. How much effort does it take for someone to get their needs met in a scenario where they don't have the full grid? And that's both the time and the money they take to get their medicine, their food, find shelter. And then also take into account ability, which to quantify, we've used median household income. But this is just an example of thinking beyond the electric grid itself to the people that interact with that grid to understand where to put resources, where to put upgrades. It's dependent on the available electric system. It's also should be influenced by the needs of the people that are in that system. Once you decide where you put a grid, you want to, say a resilience node. We work on things like planning for a balance of resources, the size of the grid, things like that, where you want an alternative, a trade-off space, and looking at multiple desires. Maybe often it's cost and sustainability to find a trade-off space so that a solution is going to be implemented. It needs to be practical. So we have this tool, other labs have other tools, but the basic premise is we do research in the future grid to understand the needs and design for the solutions with a range of stakeholders. So some other areas that I didn't touch on, I really focus on resilience planning. The grid of the future needs new regulatory and business models, proactive codes and standards, and work on the technical side for things like grid forming inverters, dynamic networks, and built-in cyber and physical security. And what problems will be solved? For example, with a PV-based fleet of resilient microgrids. It's not going to improve the resilience of the whole grid, but it can improve the resilience of infrastructures that support critical services at selected locations. You can't prevent a big natural disaster. You can't ensure the whole grid comes up, but you can try to balance in this future where you want to build in extra resilience and tie it in. So in closing, we want to plan for resilience. We've seen that as being imperative to people that we work with and stakeholders. We need practical methods, models, and tools. And renewables can play a big role. So it's really a time to think big. We want to enable a decarbonized future. We also want a resilient energy future to serve our communities and also to address, weaknesses before they happen that could lead to criticism of, future investments. With that, I'm happy to take questions as we enter into the panel. And again, thank you all for your time.
Thank you very much, Sama. That was a very good summary to finish off the presentations. So there are a number of questions that have been asked, and I'll try to go through some of them in the time we have left. So the first question is for Debra, and it says, your transmission policy doesn't allow for large disruption of transmission by weather, terrorist or military actions. Surely robustness and local islanding are major factors to include, which possibly could have been part of the last couple of presentations, but I'll get you to answer that, Debbie.
Sure. I mean, there's definitely pros and cons to all aspects of infrastructure that we're using to bolster our system. And one of the issues with transmission and distribution too can be that they can be potential objects of attack, both physically and there could be wildfires, there could be other things like that, as well as cybersecurity. So all of these things need to play into how we design and figure out how to future-proof our system while still trying to get at the affordability, reliability, and sustainability piece. So you're always balancing these three pieces, and how you kind of arrive at that conclusion is going to be some balance. Obviously, you're not going to want to gold plate things too much because then you'll destroy the affordability piece. So yeah, it's going to be a balance.
Thank you very much. I have a question here for Scott, and there's been a couple like this on batteries, but this is one. So do you think batteries are a good way to mitigate challenges caused by minimum demand? And if so, do you think utility scale, community scale, or residential batteries are best suited for it?
Really good question, and one we're confronting at the moment. There is no right or wrong answer at present time. Batteries have only rolled out residentially, or are only starting to really take off and be in the money. From a consumer perspective, we're seeing also at the grid scale a lot of rollout of really big batteries in the hundreds of megawatts, and they have important roles to play as well. So there is no right or wrong answer here. It's probably a blend of everything, but storage certainly has an important role to play.
And while you're here, Scott, I'll just go to one of the other questions asked. Does Australia have plans to transmit power into other nations to their immediate north, such as PNG, Indonesia, further west into Southeast Asia?
Look, we don't in AEMO, but we do live in a world where that is possible. So who knows what the future holds, but certainly from AEMO's perspective, we're not looking at that.
Thank you, Scott. I'll just jump to one of the later questions because it might be relevant. So this is not addressed to anyone, so I'll wait and see if either Summer or Jessica might want to have an attempt on this one. If the whole world switches to renewable energy, will it in the long run offset global warming or collectively just be as demanding maintenance-wise? Anyone would like to have an attempt at that question? It wasn't directed at anyone.
Only because you said, so I haven't answered a question, but I would say that that's outside of my research area.
Yes, try this one. Yep.
I'm sorry, did you hear me?
Yes. So.
Okay. I think I mean, this is not speaking as a researcher, it's just as reading. I mean, I think maintenance is lower with wind and solar farms. We're seeing that with some concerns about just the labor force having enough work to do. So it seems like the maintenance is lower. There's a lot of questions about minerals and the impact of the life cycle of renewables, and those are being addressed. But I think it's a good question and an area for study.
Thank you, Summer. Debra, I've got a couple of questions I'll put together. There is, how is the power transmission cost so low in the conversion to 100% renewable compared to generation? And the question from the same person, how much is the cost of infrastructure build out for 100% renewable?
Sure. So so it varies from scenario to scenario and what the different goals are. So some of the goals that I talked about were 100% clean electricity, whereas some one of the studies looks at 100% clean energy, which is a lot broader because it includes, massive electrification and use of hydrogen and other fuel pathways. But just real quick, for example, with respect to that last study that looks at 100% clean energy, the study is called 0 by 50. The transmission piece of that was 200 billion in their clean electricity scenario and 350 billion in the clean energy scenario. But again, those costs were very small compared to the generation, storage, hydrogen, and distribution infrastructure build-outs. And they also found that by building the big national transmission network, that they could save $1 trillion in decarbonizing the energy system. So it saved money in the end compared to not building the national transmission network.
Thank you. Thank you, Debra. Thanks for that response. Coming back to Scott. Is that one? Is Australia planning any pump storage systems to relieve their issues when power demand is low?
Once again, AEMO is not. We don't do that, but there are participants that are, and most notably, of course, the Commonwealth Government has a large hydro scheme in the middle of Australia, middle of the east coast, called Snowy Mountain Hydro, and that's being upgraded to allow for pump storage as we speak. And there are other smaller proponents around the market doing that as well.
Thank you, Scott. Again, I've just picked a question that, again, is not directed at anyone in particular, but it's looking at particular battery technology. And it asks the question, can somebody speak to the status of flow battery technology that does not require extraction of minerals? I'll leave that open. Does anyone want to have an attempt at that question? Nobody seems
I can just say, if nobody else wants to say anything about flow batteries, that I think flow batteries are a great technology. And I think it's very promising because it could be a potential for, long duration storage. It could get you past that 4-hour sort of point that we've gotten to with lithium ion batteries and take us much further. And as well, you could sort of transport, the flow battery liquid. And so it gives you sort of options and flexibility as well. So I think it's really promising.
Thanks for answering, Debbie. And I'll just make a comment. There is flow batteries being used in the residential market in Australia. I'm not familiar with all the other countries, but there is a local manufacturer at the small end doing 10 kilowatt hour systems. So it is starting to get some market share here in Australia. Sorry, I'm just trying to go through some of our similar questions. Apologize for this. It's because there's a number of questions that aren't aimed at anyone in particular, so I'm just there was a question for Scott. Again, it was on batteries and asking the question again. So power cell batteries becoming common. There are also major battery capacities, solar wind farms. You just said, can you analyze these in more depth? You might have sort of answered it in that when you answered the previous question, but I was just coming across this one. Well, it seems to be a very broad question, hard to answer enough.
I'm just sort of trying to understand what the question is.
There's It came in at 8:40. Yeah, so the question is, can you analyse these in more depth? And it just says, household batteries becoming more common. There are also major battery capacities at solar and wind farms. And it was sort of an open question. Can you analyse these in more depth? I suppose.
Yeah, okay.
Yeah.
So I think maybe just to talk to what's happening in Australia and what we're seeing in the way forward. The important thing about battery storage is the inverter and the ability of the inverter to form a grid. Historically, most inverters follow the frequency. Now we're starting to see better research and technology in this area, which will be really important. And if you want to look at a really good paper on this, jump on the AEMO website and look for white paper on grid forming inverters. But basically, where I think we're going is the big batteries where you can have very state-of-the-art control systems. They'll become an increasingly important part of forming a grid, and where you lose large synchronous generators as we move forward. For example, in Australia, we've got a lot of coal. So yesterday we released our integrated system plan. Once again, well worth the read from Australia's point of view to get a real understanding of what's happening. But as coal is phased out, I think we'll see more and more large batteries with these advanced inverters. And then the other thing is, on the residential side, we're seeing virtual power plant organisers and owners, what we generically call in Australia aggregators. And I think you'll start to see them play a more and more sophisticated role as well.
Thank you, Scott. Well, on that note, we've almost reached the 1.5 hours mark. So I'd personally like to thank our 4 speakers today. I think it's been informative of looking at things from a different perspective across, to be fair, just 2 countries, but I think it's relative of those studies will benefit people from other countries on seeing what's happening. So unless Arabella has anything more to say, I'd say that's it, and thank you very much to everyone.
Yes, thank you, Jeff. I do have one tiny bit more to say. First off, I want to say thank you to all of the presenters joining us today. Thank you very much for all of your valuable presentations, and I do think the audience quite enjoyed the webinar. For my final announcement, I want to share that this webinar has been recorded, and the recording is going to be available on the ISES homepage within a few days after the webinar. We need some time to edit, but then it's going to be up there. And for our ISES members, please remember you already have unlimited access to all past ISES webinars and presentations in the ISES members area, where you can just log in with your login details. So from that side, it's all from my side. If you want to share your feedback on the webinar, please do so at public.relations@ises.org. We always look forward to your comments or questions you want to share with us. And there's a tiny feedback survey coming your way at the end of the webinar. So if you wanted to complete that, that would help us a lot as well. And with that, I think we're good to close. Thank you everybody again for joining us, and we will see you again next year, because this has actually been the last webinar for 2021 from our side, but we are going to be back, we're going to be stronger in January. So yeah, please join us again, and we're looking forward to that. Thank you everybody, and goodbye.